It took more than 2 complete decades of collaboration between some of the brightest minds working at NASA, the European Space Agency, and the Canadian Space Agency, as well as outside these organizations, in order to create one of the most complicated pieces of equipment in the world. It should not come as a surprise that the scientific community and the general public have reacted with excitement and jubilation to the release of the first picture taken in full color by the James Webb Space Telescope just about a week ago. The unveiling of the photograph was presided over by President Biden, Vice President Kamala Harris, legislators, and other high-ranking NASA officials, as well as scientists and engineers. However, the journey to the sky that the James Webb Space Telescope undertook was a challenging one. Let's learn about this journey in this video. At a workshop held at the Space Telescope Science Institute in September 1989, where scientists came together to discuss the successor to the Hubble Space Telescope, the idea for what would eventually become the James Webb Space Telescope was conceived. This occurred before the Hubble Space Telescope was even launched into space. Originally referred to as the Next Generation Space Telescope, scientists came to the conclusion that in order to look back in time to observe the faintest light from the time when the first stars, galaxies, and protoplanetary disks were forming, as well as search for signs of life on distant planets, they would need a space telescope that was distinct from the Hubble Space Telescope, which observed light in the visible and ultraviolet spectrums. This led to the development of the JWST. Scientists needed a telescope that was sensitive to infrared and mid-infrared light. According to the consensus of the scientific community, the Big Bang, often known as the moment when the universe began, took place 13.8 billion years ago. And ever since that time, the cosmos has been expanding at an ever-increasing pace of exponential growth. The earliest stars and galaxies after the Big Bang have moved away from us because of the expansion of the universe. As a result, the light that they have emitted, that has yet to bridge the cosmic void and reach us here on Earth billions of years later, has redshifted to such a degree that it is no longer visible to human eyes due to a phenomenon known as the Doppler effect. The phenomenon known as redshifting occurs when the source of a light moves away from you, or in this case the planet Earth, causing the wavelength of light to stretch out and become longer. As a result, the light that is emitted by the source is seen as shifting towards the infrared spectrum, giving it a red color. The decade of the 1990s was devoted to the investigation of whether or not the JWST would be possible, as well as the development of the technological components of the telescope and the selection of partners and worldwide collaborators who would work on this project. In honor of the second administrator of NASA, James Webb, who was important to NASA's manned spaceflight program in the 1960s, the Next Generation Space Telescope was formally given the name James Webb Space Telescope in August of 2002. Construction on the James Webb Space Telescope began in March of 2004. However, in 2011, as a result of delays and reevaluations of the budget, the United States Congress conducted discussions in which they accused NASA of mismanaging and threatened to cancel the James Webb Space Telescope project. To the relief of the scientific community, NASA was able to keep the JWST project moving forward, and the observatory's construction was successfully finished in 2016. The James Webb Space Telescope is visually distinct from any other telescope that has ever been constructed, and for a good reason. It breaks new ground in scientific research in ways that have never been seen before. Its primary mirrors have a diameter of 6.5 meters, compared to 2.4 meters for the Hubble Space Telescope, so that it may gather as much light as possible from the most distant and weakest stars, galaxies, and light that is reflected off the atmospheres of different planets. The mirror is composed of 18 smaller hexagonal mirrors that are all made out of beryllium, which is a material that is 6 times as strong as steel, but only has 1/3 of the density of aluminum. These mirrors are coated in gold and joined together in a honeycomb pattern so that the mirror can function as one large mirror. It was built with such precision that, according to Scott Wilby, who is the JWST program manager at Northrop Grumman, it has an error of 15 nanometers, which is the size of a bacteria. Its sensors are so sensitive that if they were used from Earth, they would be able to detect the heat signature of a bumblebee flying on the moon. After being reflected off the primary mirror, the light is next reflected off the secondary mirror, and then it is reflected off the tertiary mirror, so on until it reaches the Integrated Science Instrument Module, which is where the JWST's most important instruments are housed. The near-infrared camera, known as NIRCam, the mid-infrared instrument, known as MIRI, and the 2 infrared cameras that make up the ISIM. Both of these cameras were developed by the European Space Agency in collaboration with NASA's Jet Propulsion Laboratory. The ISIM also includes 2 spectrographs, the near-infrared spectrograph, known as NIRSpec, and the Fine Guidance Sensor, or near-infrared imager. Together, the instruments that are situated behind the primary mirror have the ability to detect infrared red lights with wavelengths ranging from 0.6 microns to 28 microns. This gives them the ability to look through dust clouds and view bright bodies that are located behind them. And according to NASA, spectrographs are able to identify the physical attributes of the bodies, such as their mass, temperature, and chemical composition. This enables researchers to study a great deal more about what early stars were formed of and how they evolved. The Wonder can also investigate whether or not planets in the far reaches of the galaxies have the telltale signs of life by searching for atoms and compounds that are released into the atmosphere of these planets by living life forms. Because these instruments are so sensitive, the scientists know that it would not be possible to operate the satellite in low Earth orbit as the Hubble Space Telescope does. This is because the sensors detecting infrared, which is emitted by warm bodies, would be overwhelmed by the heat from both the Earth and the Sun. Instead, the James Webb Space Telescope would have embarked on a journey to inter-orbit around a point in space known as the Lagrange Point 2, or L2, which is about 1.5 million kilometers distant from the Earth. Even at that location, the sun's rays have the potential to raise the temperature of the equipment to more than 100 degrees Celsius. This is where the passive cooling mechanism of the heat shield the size of a tennis court comes into play. It has 5 layers. Because it is pointed towards the sun, the optical portion of the telescope is protected from direct sunlight, and the temperature in this shaded area drops to minus 230 degrees Celsius. The engineering of the telescope was further complicated by its massive size, which meant that, in order to fit inside the nose of the Ariane 5 rocket that was launched from Kourou in French Guiana, it would have to be folded down and then unfurl in space when it reaches L2 in order for it to be able to make the journey. As a result of the great distance that separates us from the James Webb Space Telescope, there is currently no strategy in place to repair or maintain the instrument in the event that something goes wrong. With the amount of fuel that it has, JWST is only expected to function for 5 years, but NASA is hoping to get an additional 10 years out of it. In fact, a micrometeoroid has already collided with the James Webb Space Telescope, causing it to sustain some damage. NASA is currently evaluating the situation. Despite this setback, the most recent photographs of SMACS 0723, the Southern Ring Nebula, the Carina Nebula, and WASP 96b that have been released by the James Webb Space Telescope have already revealed features that were previously unknown to us. Stephan's quintet is also one of the objects in these images. A photograph of the Southern Ring Nebula has shown a second dying star that was previously hidden within the nebula and which we're unable to detect. The spectrograph that was on board the telescope made the discovery that the alien world WASP 96b contains water in its atmosphere, and this is just the beginning of what scientists hope to learn about it. We will be able to study the first stars and galaxies, look at the evolution of galaxies by comparing the oldest galaxies with newer ones, and see how the first planetary systems were formed thanks to the James Webb Space Telescope. And maybe, just maybe, it will tell us a little bit more about our role in the universe, as well as ultimately answer the question of whether or not we are alone in the universe, which will hopefully inspire future generations of thinkers. That's it. Make sure you give this video a thumbs up and also click on that subscribe button to enjoy more exciting videos. Thanks for watching.